So last time I mentioned that definition here. Look at the definition. 0 factorial equals 1. Yeah. Yeah. So this assumption looks a little, weird because it's not easy to see that, right? Yeah. For most people, they may feel 0 factorial looks like 0, yeah, but why here 0 factorial is defined as 1? Yeah. All right. So here, let me explain. Try to give you the first round understanding. The second round next slide we will use a formula to see it. Yeah. So the first round we use our general understanding to see it is reasonable. Yeah. All right. So when you look at the factorial definition here, it is a sequence of multiplication, right? Yeah. Here, think about when we do our programming, when we need to calculate a number that is a sequence of multiplication, how do we do it? Yeah. Here, I'm talking about when you write your code in a program. Yeah. So usually we create a variable, right? So here, let's assume I use an integer variable called a product. Product equals 1. Yeah. So that's my initial value, right? Because when I do multiplication, my initial value should be set to 1. Because 1 times any number equals that number, right? So here we use this property. 1 times A equals A property. Yeah. So that's the reason we set our initial value 1. Okay, all right. Then we use a for loop. Inside the for loop, we update product equals product multiply, let's say, the current value of the array. How about that? That's the typical way we write our code to get a product of a sequence of numbers, right? Yeah. So here, let's look at from this point of view. All right. When we do this calculation, now, if you look at the 0, 0 means we do not do any multiplication, right? Yeah. 0 factorial. That means in this sequence of multiplication, we do not do any. We do 0 multiplication. If we do 0 multiplication, that means the initial value is used as the product number, right? So the initial value, that's why the 0 factorial, here we take the initial value. Right? So this is, our first round understanding. Yeah. 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 Based on this understanding, because when we do summation, yeah, a similar thing we do, when we do summation, we use the variable sum, but our initial value is 0, right? Yeah. And in our for loop, every time we will do for loop sum equals sum plus a of I, like that. Okay. And for the summation case, initial value is 0, not 1. Okay. Yeah. The product case, initial value is 1. So that's the reason, you can see, yeah, this assumption is quite reasonable. Okay, yeah. All right, yeah. So the next slide, we will see a rigorous proof of this one. Yeah. All right, so let's look at the next slide. This time, now we want to use the divide and conquer. recall the last time I explained the basic divide and conquer approach. Yeah. In our method 1, we just use a for loop to calculate factorial. But here I want to use this as a simple example to explain how to do it. Yeah. Solve the same problem using divide and conquer. So get ourselves familiar with that, the typical divide and conquer approach. Yeah. All right. So when we start, first, let us define a function. Here, let's call it f of n, capital F of n, as this factorial function, f of n. Yeah, because in order to do recursion, we need a function. We need to have a known function. Yeah, because we plan to do recursion in this implementation. Yeah. All right, so next, now we do the divide step. When we do the divide step here, we divide along this line. That means we cut off the last element. Yeah. So here we have n elements, yeah, as our data. But we divide our data into two parts. Yeah. The smaller one, the smaller part, just one element. Yeah. So that is one of the ways to divide our data. Yeah. Just one element reduction. Now here you can call it one element reduction. Yeah. Size 1 reduction. Yeah. All right. So after this reduction, yeah. So let's look at the two parts, right? Yeah. The larger part, you can see we can still use the same f function to represent it. It is still a factorial, but it is a factorial with n minus 1 consecutive integers. N minus 1. Yeah. So we use f of n minus 1 representation. Yeah. Then, remember last time I mentioned we have a problem solving approach. We approximate the original problem, then we bridge the gap. Yeah. So here, this is the approximation of the original problem. F of n. Calculate f of n. That's the original problem. But now, we calculate an easier version of the original problem. F of n minus 1, we treat it as an easier version of original problem. And we assume we have it. We assume we have it, yeah, based on the recursion. Yeah. How do you know you have it already, right? Yeah, based on the recursion, we have it. Okay? Yeah. That's the power of recursion. Yeah. That's the importance of recursion. So we can assume we already have it. Yeah. Then bridge the gap. The gap is this part. Yeah. The one element reduction, that part is the gap. So we bridge the gap. Okay? Yeah. All right. Then the recurrence relation. Yeah. F of n equals f of n minus 1 times n. Yeah. So we can get a recurrence relation formula. Yeah. Then when we write our implementation, we just write a recursive function implementation using this formula. Yeah, I think everyone can do it. Yeah. So here we just use a different way. We do not say this way is better than the first way. No, actually the first, if we look at the efficiency, computation efficiency, the method 1 is better than this one. Okay, method 1, the for loop 1, better than this one, this is method 2. Better than this method 2. Do you know why? Do you know why here we say method 1 better than method 2? Yeah. I talked about this last time. The reason is method 1, it uses less memory resource. Okay, it uses less memory resource. Yeah. Method 2, because recursion, in general, we need to use more memory resource. Yeah. So why recursion use more memory resource? So why recursion uses more memory resource? Okay? No. It relates to recursion implementation. Do you know how is the recursion implemented in computer main memory? Yeah. So right now, high-level languages all support recursion. Yeah. But how to implement it in a high-level language? Yeah. So it uses a data structure. It uses the data structure called a stack data structure. Okay, stack, you know the stack, right? Yeah. Looks like this. So you push the data into the stack, and it has the property first in, last out. Okay, the stack has a property first in, last out property. Stack. Yeah. All right. Yeah. So let me delay this stack details later. Yeah. So today here I just say recursion uses more memory resource, and the reason related to the stack, and so why the stack way consumes more memory resource. I delay it to later, because later we will, when we talk about efficiency, we will get to this question again. Yeah. All right. So now we can do the implementation, but I want to use this formula. Yeah. So this formula here to explain that n 0 factorial equals 1. Yeah. Yeah. Because here, if we use this formula here, yeah, then it's very easy to understand. So we can see clearly, yeah, it is correct. Yeah. All right. Here, let's write, yeah, this way. Yeah. So we do division, yeah, because here we assume n greater than 0. So n cannot be 0. If n cannot be 0, we can do division by n, both sides of the equality, right? Yeah. So after we do the division by n, so we get this formula. Yeah. Then let's plug in n equals 1 into this formula. So you can see the left-hand side f of 0 equals right-hand side f of 1 over 1. And f of 1, it is 1 factorial. 1 factorial, we know it is 1. Okay? So 1 over 1 is 1. Yeah. But the left-hand side, f of 0, based on our original function definition, f of 0 is 0 factorial. So that means 0 factorial equals 1. Yeah. So in this way you can see, yeah, It is correct. Yeah. Yeah. All right. Yeah. So here, the conclusion. Yeah. From this simple example, although it's not necessary, we use the recursive algorithm to solve the factorial problem. Yeah. Actually, the recursive way is a little worse than the iterative way. Yeah, yeah, yeah. But here we use this simple example as a, simple learning example. Yeah. So we want to learn the concept. Yeah. So it's a learning process. Yeah. All right. And we can see it's an interesting way to solve the problem. Yeah. Yeah. All right. Before we move to the new question, I want to explain one thing. Yeah. One thing. Yeah. Because here I say the recursive implementation is a little worse than the iterative implementation. Some of you may ask why we use recursive method instead of iterative method. Yeah. The answer is simple. The answer is we want to take advantage of the power of recursive algorithm. It's very powerful. Yeah. What do you mean powerful? Powerful in problem solving. Yeah. You can use recursive algorithm to solve many relatively hard computing problems. That's the biggest advantage of recursive algorithms. To show you that, let's move to the next topic. I want to show you the power of recursive algorithm. Yeah. Yeah. Here I give you one example. Let you see the power. Okay? Yeah. All right. So the question, yeah, I think it's a puzzle question. Yeah. I think you saw this puzzle before. Yeah. But here, let us use the recursive algorithm to solve this problem. Yeah. All right. Problem number 7, Tower of Hanoi problem. Yeah. So we want to solve a puzzle problem like this. Yeah. Yeah. In this example, you can see there are 3 disks. Yeah. Yeah. But in this question, we want to solve an n-disk question. Yeah. Yeah. When I use a diagram, so it's a little easier to use a simpler version. So here, in my diagram, I just use 3-disk version to explain the main idea. Yeah. But our goal, we want to solve n-disk problem. How to solve n-disk problem. That's our goal. Okay. Yeah. All right. So let's look at the rules. Yeah. Let me recall a little bit. Yeah. You may forget the details. Yeah. So there are 3 rules when you move a disk from one peg to another peg. Yeah. All right. The rules. Number 1, only one disk can be moved at a time. Yeah. Yeah. In order to calculate efficiency, computation efficiency, we want to count the number of disk moves. Yeah. So each disk move, you can only move one disk from one peg to another peg. Yeah. All right. Number 2, a disk cannot be placed on top of a smaller disk. Yeah. So you have to, follow the order. The larger one, lower, smaller one on top of larger one. We cannot do the opposite way. You cannot place a larger disk on top of a smaller disk. Yeah. So the second rule. Yeah. All right. The third rule, all disks must be stored on a peg except while being moved. Yeah. So rule number 3 means, yeah, because when you make moves, you are not allowed to put a disk on the table. Okay? Yeah. Because if you are allowed to use disk on the table, then we can arrange all our disks on the table. Then it's too easy to, to solve the puzzle problem. Yeah. So rule number 3 does not allow you to store any disk on a place other than the pegs. Yeah. One of the pegs. Okay? Yeah. All right. So if you follow these 3 rules, then the puzzle is challenging. Yeah. In order to solve the puzzle, yeah, you need to make some effort. Yeah. Not very easy, a little challenging. Yeah. All right. So here, let's try to solve this 3-disk version first. After we solve it, yeah, then we need to extend our solution to n-disk solution. Yeah. All right. Yeah, here I give you the reference on the textbook. Yeah. All right. Analysis. How to solve the general problem with n disks. This is our goal. Okay. Yeah. Keep in mind that's our goal. All right. But first, you can see solving the n-disk problem, it is hard, right? Yeah. Do you feel hard? Yeah. Yes, it's hard. Okay. Yeah. I believe everyone feels it's hard for the n-disk problem. Okay. Yeah. All right. Now, recall, in this situation, when we need to solve a relatively hard computing problem, do you still remember there is one simple strategy we can use in this situation? Yeah. We used it a few times before. Yeah. Yeah. We used it a few times before. Here we need to use it again. Some simple strategy. Do you still remember that? Any of you? Yeah. Yeah. Because n disks, too many disks, right? Yeah. So it's hard to see it clearly, right? So in this situation, there is a simple, effective strategy. We do experiments with n relatively small, where n is a small number. That's easy, right? Yeah. We just work on a few experiments and we assume n is small. Okay? Then it's easy to solve. Think about it. When n equals 1, is it easy to solve? You only have one disk. Yeah. You just move that disk to the destination peg. Then you solve it. One move. Yeah. Then you think about n equals 2. Yeah. Yeah. 2. You have 2 disks. 2 disks on 3 pegs. Yeah. 2 disks. You have 3 pegs. Then it's also easy, right? Yeah. Yeah. You move the top disk to a temporary peg. Yeah. Not your destination peg. Temporary peg. Then the lower disk to the destination peg. Then move the top one back to the destination peg. Then you solve it. So n equals 2. You can also solve it easily. Yeah. All right. After that, now we need to look at n equals 3 case. Yeah. All right. So here. Yeah. Now, our goal, we want to solve the 3-disk problem. Yeah. So when we solve the problem of size 3, we can assume that we have already solved the problem of size 2. Yeah. Let's use our recursive thinking. Recursive thinking we used in the factorial problem. Recursive thinking. Yeah. When we need to solve a problem of size 3, we assume we already have the solution of the subproblem with size 2. Yeah. Because we can do it easily. So that assumption has no problem here. Yeah. All right. Yeah. So now, based on that, we only need to fix the difference between these two problems, the problem 3 and the problem 2. Yeah. The problem of size 3 and the problem of size 2. What's the difference between these two problems? Yeah. If we can handle the difference between these two problems, then we can solve the whole problem of size 3. Yeah. That's the idea. Okay. Yeah. All right. So here, let's do some work. Yeah. So let's do some experiment. Yeah. 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 Because it's hard to see it, right? When n equals 3, if we only use our thinking in our mind, it's still too hard. Yeah. It's hard to see it. Yeah. All right. So we need to do it on a scratch paper. Yeah. For example, here I draw some diagrams. Yeah. Step 0, before we move any disk, this is the state before we move any disk. Yeah. All right. Now we can make our first move. That's easy. The top disk, move it to the, one of the two remaining empty pegs. Empty pegs. Yeah. The first move. Second move, the middle one on peg 2. All right. Yeah. All right. The third one, yeah, because here we cannot move the third one, right? Yeah, because the third one is the largest, the third disk largest. We cannot place it on top of smaller one. Yeah. So it has to stay on the first peg. Yeah. But we can make room for the bottom peg, right? Yeah. So we can move the smallest one to peg number 2 to leave an empty peg for the bottom peg. For the bottom disk. Yeah. So this peg number 3, we treat it as our destination peg. So now we move the largest disk to the destination peg. Yeah. But here you can see the situation. What you see in peg number 2, that's the solution of P of 2, right? Yeah. We just did a solution of problem size 2. Yeah. So you can treat what we did in this way. We apply the solution P of 2 first. So this is the solution P of 2 first, to move the top 2 disks from first peg to the second peg. The second peg we treat as the temporary peg. So we apply the solution to the problem of size 2 from the starting peg to the temporary peg. That's what we did so far. Yeah. Now, fix the gap. Remember, there is a gap problem we need to fix that gap part. Yeah. Now let's do that part, the gap part. This time we can move the largest disk to peg 3, the destination peg, peg 3, yeah, the largest. All right. After that, we need to move the top 2 pegs to the destination peg, right? Yeah. So we need to do a few more moves, disk moves, a few more. But when we do that, can you see we just apply the solution to the problem of size 2 another time to move the 2 disks to the destination peg? That's the solution of P of 2 again. Another P of 2 solution. Yeah. But here we fix the detail. The detail, move the smallest peg to peg 1, the middle disk to peg 3, and the smallest peg to the destination peg. And we find a solution of P of 3. So this is P of 3 solution. Okay? So you can see we need to make this many moves to solve the whole problem. Yeah. So that's the detail of the solution in this diagram. Yeah. Yeah. All right. So after we have this experiment, we want to generalize what we did in this P of 3 solution to P of n solution. So our goal, we want to generalize the solution from P of 3 to P of n disk. P of n disk, how to do it. Yeah. So the next step, all right, we want to, modify, or we want to at least we want to formulate this P of 3 solution, modify it slightly to get a P of n solution. Yeah. Now, let's do it here, the general case. Yeah. Yeah. And the general case here, so you can see for P of n, it could be very complicated. It could be very complicated. Yeah. All right. So how can we solve such a complicated computing problem? Here, the main point is using recursion. We can solve it. Yeah. Because when we solve, yeah, so the goal, we need to solve P of n, but we can assume P of n minus 1 available. P of n minus 1 is available, sorry. Yeah, because one student won't get in, so yeah. Let me, yeah. Yeah. All right. Yeah, so let me write. P available. Okay, available. No. Yeah. Then it's not that hard because we know P of, if we can assume P of n minus 1 available, the solution, then it contains large number of disk moves in this solution. All right, so we already have it. We already have this part. Now we only need to fill the gap between P of n and a P of n minus 1. That gap part is not that hard. That gap part, just small number of disk moves. Yeah. So let's look at that. Yeah. All right. And here you can see, here we use the problem size reduction. We reduce the problem size from n to n minus 1. Yeah. The n minus 1 case, we assume we have it. We can use that solution directly. Or we can use that solution by recursion. Yeah. So here the idea, we use P of n minus 1 solution by recursion. Yeah. That's the power. Yeah. That's the power in problem solving. Yeah. All right. Here, let me modify the previous diagram to make it for a version of n-disk problem. Yeah. Here, because it's hard to draw n disks, so here let's imagine this stack of 3 disks as n disks. Yeah. Just imagine it. This time there are n disks on peg 1. Yeah. All right. Now, in order to solve the whole problem, because we already assume we have the P of n minus 1, so we can move the top n minus 1 disks from one peg to another peg, to the temporary peg, from the from peg to temp peg, but just the top n minus 1 disks. Yeah. All right. Yeah. So in order to get that, so first let's solve. This is a Pn minus 1 solution. Okay? Yeah. Yeah. So let's apply that known P of n minus 1 solution. Yeah. We know by recursion. We can assume that. Yeah. Recursion allows us to get the solution result of P of n minus 1. Recursion. Yeah. Yeah. So we can assume that. Yeah. For the detail, yeah, if some of you are still not quite sure how does the recursion can give us the solution of P of n minus 1, yeah, I need to use the stack data structure to explain the recursion implementation. Yeah. So we will see that later. Yeah. Stack. Yeah. And for you only need to know your programming language supports recursion. So if you just make the recursive function call, you get it. You get the result. You don't worry about it. Yeah. Because your programming language allows you to do it. Yeah. It would work. You do not worry about it. Yeah. So here, that's the reason we can assume P of n minus 1 already available. So we apply that solution here by the recursive function call. Yeah. Then the get part. Move the bottom disk. Move the bottom disk from. Yeah. So here. Yeah. Yeah. So I need to draw a little bit. The next bottom disk from the peg 1 to peg 3. Then after that, these n minus 1, another P of n minus 1 solution to move the top n-1 disks to the destination peg. Yeah. So you can see that's the whole solution. That's the whole solution. Yeah. So we apply P of n-1 twice. Between those two recursive function calls, we move the bottom disk from peg 1 to peg 3. That's the whole solution. Okay? Yeah. So if you can see that structure, that's the structure of the whole solution. If you can see that, then we need to write a recursive function implementation here as the pseudocode. So here, let me explain the pseudocode. So here we call the function called a move disks function. In this function, there are 4 parameters. The first parameter, integer parameter num, the number of disks, that's the n. Okay, n disks, n. Okay, then 3 integer variables representing 3 pegs. Yeah. Peg 1, peg 2, peg 3. Okay, yeah. So from peg, yeah, 3 integer parameters. Yeah. So then, in first, we assume the number of disks positive integer. Yeah. Then in the body part, yeah, the main body implementation, yeah, only 3 statements. 3 statements. The first one, we call this function recursively for n-1, the problem size n-1, recursive function. Yeah. But the order of the 3 pegs should be changed slightly. Yeah. Because the first, when we apply the solution of P of n-1, we want to treat this 10 peg as the destination peg. Yeah. So we put temp peg variable, pass temp peg variable as the third parameter. That means we treat it as the destination. And the second one, the temporary one, the 2 peg, we treat it as the temporary peg. Yeah. So that's in this recursive function, we do that. All right, then move the bottom disk. So this one, we output a message. message. So this is, we use this message to represent that we move the bottom disk. Okay, all right. After that, then we need to do another recursive function call on that n-1 disks, but this time the starting peg is that temporary peg. Okay, the temporary peg, this time it becomes the starting peg. Yeah, because we put n-1 disks on that temporary peg. Yeah. All right. Then 2 pegs still the destination, but this time the from peg is used as the temporary peg. Okay? So when we, after this arrangement, we apply the n-1 solution another time, and we know, based on the diagram in the previous slide, we know we would get a complete solution in this way. Yeah. How about the solution? Yeah. You can see the whole implementation of this puzzle problem, only these a few lines, very short. The code is so short, but it solves pretty complicated puzzle problem. That's the point I want to show you. You have seen the power of recursion, power of recursive algorithms. You can think about, if you do not use the recursion here, can you solve the puzzle problem? It will be too hard. Yeah. 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 And there are many hard computing problems in the real world. You need to use the recursive algorithms to solve, just like this one. Yeah. Okay? Even if we know recursive algorithms usually uses a lot of computing resource, even if we need to use a lot of precious memory resource, because it is so powerful. So we just take it. It is so powerful. We are willing to spend that much computing resource, and we want to solve a hard computing problem using the recursion. Yeah. That's the story. Okay? Yeah. Any question? Yeah. For this example, any question? Yeah. So here, after we solve the problem, there is one last question here. Yeah. Question. How many disk moves for P of n? Okay? We didn't calculate that. So how many disk moves, total disk moves, do we need in order to solve P of n, size n? Yeah. How many disk moves do we need for P of 3? P of 3. Any of you see it? Any of you? So let me move, go to the previous slide. I need to back to this slide. Okay. 1, 2, 3, 4, 5, 6, 7. This is the last move, 7. Yeah. So the answer is, if n equals 3, the answer is 7. Answer is 7. Yeah. But if the size is n, what is that number? Yeah. Think about that. Yeah. Here, I do not give you that number. Yeah. Yeah, because later I will show you how to find this number. How to solve a recursive relation to find this number. Later we will do that. Yeah. All right. Yeah. So here, so we finished that topic. The next one. Now we move to part B. Yeah. The title called variable size reduction. Yeah. Yeah. Remember, in the previous two examples, factorial example, the Tower of Hanoi problem, those two examples, we do problem size reduction by 1. Size 1 reduction. And here, I want to show you another variation of the problem size reduction. So it's called variable size reduction. The size, every time when you reduce the problem size, that size can vary, sometimes larger, sometimes small. So variable size reduction. Yeah. All right. B.1, reduce problem size by half. Half size reduction. Okay? Yeah. So look at the example. Problem number 8. Count binary digits. Yeah. Given an integer, so we want to count the number of so digits, yeah, binary digits. Binary digits, actually it's the bits, right? We want to count the number of bits in the binary representation of an integer n. Yeah. Given a positive decimal integer n, find the number of binary digits in its binary representation. Yeah. So it's not very hard, yeah, but here we want to see that half size reduction. That variation. All right. Yeah. Analysis. First, let's review binary representation a little bit. Yeah. So in your discrete math, so you have a section, yeah, you know, explaining this binary representation. Yeah. So let's use the, you know, the basic formula there. Yeah. How to represent a decimal integer n in the binary representation, base 2. Binary, that means the base is 2. Base number is 2. Yeah. And the bits. So here the coefficients. So that's the bits we use to represent this integer, yeah, in the binary form. Yeah. And the most significant bit, so this is the most significant bit, should be non-zero. Yeah. Otherwise, if it's 0, then we can reduce the you know, the size, right? So we can simplify it. Yeah. So we look at the next bit. Yeah. So we want to find the first non-zero bit corresponding to the, you know, power of 2, yeah, term. Yeah. Power of 2 term. Yeah. All right. So here we assume b sub s equals 1. Yeah. So now we can see from this formula, if we do the counting, yeah, the answer should be s plus 1. Yeah. Because here, if we use the subscript, we count subscript 0, 1, 2, consecutive integers through s, and we get s plus 1 numbers. Yeah. Yeah. So that many bits. Yeah. So the answer is s plus 1 bits. Yeah. But the question is, here we use the s. Yeah. Our answer is s, but we should represent it in terms of n. Okay? We want to represent s in terms of n. Yeah. N is the given number, so we know it. But that s, we need to find it. We cannot see s immediately. We need to find that s. Yeah. So in our final formula, we want to write this answer in terms of n, not containing s. Yeah. So we need to find that representation for s. Okay, all right. Yeah. How to find s? Now we need to do some data processing work, yeah, in order to find s. Yeah. All right. From n, yeah, so let's look at the data manipulation steps in order to get s. Yeah. The insight. Yeah. Yeah. In order to find the relationship between s and n, yeah, we need to do this. Use a transformation to change the structure. We need to work on the structure. We need to manipulate the structure and try to extract some useful information in our transformation. All right, so here we use the division operation. Because here, look at the structure. We have many multiplications in each term. So one way to change its structure, we can use integer division or division by 2. Division by 2 operation. Okay, all right. So let's do division by 2 operation on the original formula. Original n representation formula. So the left hand side, and we do integer representation. So we take the floor function as the integer representation, n over 2 floor function. We only keep the integer part. So we do not keep the fractional part. So then b0 over 2 is gone, right? b0 over 2. So no matter b0 is 0 or 1, because that's the fractional part. So that term is gone. So the remaining term, but we need to do division by 2, so we have this representation. Okay. Now, when we compare this representation with our original representation, compare those two, you can see some relationship, right? So you can see some nice property. All right, So here, the left-hand side. Let's look at left-hand side. Left-hand side, that's our current problem size, right? Our current problem size. Because if you look at the left-hand side, we want to represent this integer, left-hand side integer. It's still integer, positive integer, okay? So when n is relatively large, so you can see the current formula, basically it is just a binary representation for this floor function of n over 2. Binary representation. This is its right hand side, is its binary representation. Okay? And you can count the number of bits. The number of bits, right hand side equals s, right? The total number of bits equals s. So look at the subscripts, 1, 2, 3, consecutive integers from 1 through s. That's s. So now, conclusion. So what's the conclusion? From these two equations, we want to get a conclusion formula. So what's that? All right. First, the least significant bit is moved, b0. So when you do the transformation, it is gone. It is moved. Okay? Second, the number of bits is reduced by 1. Because from s plus 1 to s, reduced by 1, the number of bits. The data size is reduced approximately half size, right? The current problem size becomes 1/2 of the original problem size, approximately 1/2. So you reduce the problem size by half, but the answer is reduced by 1. All right. So the problem size is reduced by half. So that's the observation from the transformation. So as a result, we get a recurrence relation. So this is a recurrence relation. If we use this bin rec, okay, yeah, binary representation recursive function bin rec of n equals bin rec of floor function of n over 2 plus 1. Yeah. Because the difference is 1. Look at the difference between these two problems is 1. Yeah. So we get this recurrence relation. Okay? Yeah. 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 And we can use this recurrence relation to solve this problem. Okay? Yeah. So we can write a program, do the recursive function call, and we can get the answer. Yeah. All right. Yeah. But next, yeah, so here we have the base case. This is the base case. Yeah. When n is 1, the number of bits is 1. Yeah. Yeah. So when you have a recursive formula, you need a base case. Yeah. Sometimes you may need more than one base cases. Yeah. Later, when we calculate the Fibonacci numbers, yeah, so we need more than one base cases. Yeah. All right. Yeah. So now, the last step, we need to solve this recurrence relation. We need to solve it mathematically. Okay. So I just talk about we can write a computer program to find the answer of this recursive function. Yeah. But another way, we can solve it mathematically. We can find a concrete math formula for this function, recursive function. Yeah. All right. Yeah. So here there is a interesting problem-solving method, commonly used problem-solving method. Yeah, it's quite useful. So I want to use this example to show you that problem-solving method. Yeah. In this situation, there is a very useful problem-solving method we can use to find a solution of this recurrence relation. Yeah. All right. Yeah. So division, we just treat left shift operation. Integer division, left shift operation, representing the floor function of n over 2. Yeah. So shift operation. Yeah. Inside computer, the shift operation is very fast. Yeah. Because inside computer, if you do the division, if you do the general division, it could be very slow. General division. Yeah. So here, yeah. Inside the computer, yeah. So here, let me talk about, a little bit background knowledge. Yeah. Remember in our first computing problem, evaluate polynomial. In that one, we make assumption on addition and multiplication inside computer, right? Yeah. So when we do addition, we use 1 unit, 1 time unit. Multiplication, we use 10 time unit. Okay? All right. So here, let me give you some rough relationship about the execution times for the basic operations. Yeah. So inside CPU, yeah. Inside CPU, yeah, we do these basic operations, arithmetic operations: addition, multiplication, and division. We only look at these 3 operations. Yeah. If addition, we use 1 unit. Okay, yeah, this unit, certain number of nanoseconds. Okay, certain number of nanoseconds, approximately 2 nanoseconds. Okay, so that U approximately equal to 2 nanoseconds. Okay, all right. So addition, we need 1 unit, time unit. Okay, all right. Multiplication, approximately 10 units. 10 units. All right. Yeah. Then division, we need to use 20 units. That's the approximate amount of time you need inside CPU. So you can see the ratio, the scale for the approximate computation time. The difference is pretty big. Yeah. Yeah. But here, division by 2, it is not a general division. It is not an arbitrary division. It's a special division. Division by 2, we know inside computer we use the binary representation. So when you do division by 2, you can shift the, decimal point. So not, let's call it binary point. You can shift the binary point to the left by 1 position. That left shift operation, even faster, this shift operation, faster. Oh, why so low? So slow. Even faster than addition. Okay, see? Addition, you use 1 unit, you use approximately 2 nanoseconds. Here, you only use 1 nanosecond. You can do that shift operation by 1 nanosecond. How about that? Okay? That fast. 1 nanosecond. Yeah. So here, I got a freeze, Yeah. Yeah, I couldn't write. Yeah, anyway, let me look at the time. Yeah. All right, so let's take a break and come back at 7 o'clock. Yeah. So then I need to fix this freeze problem. Yeah. So my screen is freezed. Yeah. Let me fix it. Yeah. So you just take a break now.